Are you terrible at concavity? Don't understand how to do concavity or what an inflection point even is? Well, don't worry. I'm a certified masterclass in concavity problems, and by the time you are done watching this, you will be 100% beast at knowing how to solve concavity problems or your money back guaranteed. If you don't know, I used to be a young, humble lad who didn't understand anything about concavity. This is what my nose looked like in class for concavity. I didn't understand anything, and that's until I looked at a Desmos graph for 8 minutes, and that's when I realized concavity is not that hard. So I'm here to share my knowledge with you guys. First, some derivative review. Derivatives show how much a function rate is changing. We know that when a function f is increasing over an interval, the derivative, or f prime, is positive over that interval. Now if f was decreasing, f prime would be negative. If f was constant, f prime would be 0, since there is no increase or decrease. Now, this is a good segue right into minimum and maximum review. Remember, when f prime crosses from negative to positive, it has to touch 0, and that's when the function becomes a minimum. F prime goes from positive to negative instead, and that's when it becomes a maximum. The reason for this is because the function just comes to a halt and switches directions. So you gotta be careful when it goes positive, touches 0, but still stays positive. It's a critical point, but isn't a maximum. Same thing applies for negatives and minimums when it still stays negative and doesn't go positive. Okay, take all of this into consideration, and now we move into concavity. Concave up graphs look like this. Concave down graphs look like this. Whoa, awesome. Take all that we learned from the graph of f, the first derivative, and now we have the second derivative. Second derivatives show the rate of change of the first derivative. So f prime increases, f double prime is positive. F prime is decreasing, f double prime is negative. F prime is neither, is just a constant. F double prime is 0. It's like f prime equals 0 for a critical value, f double prime equals 0 for an inflection point. And inflection points is when the concavity changes. You can also sort of see it as a min and max of f prime. When f prime changes direction, the concavity changes. Oh right, and the graph is concave up when f double prime is positive, down for negative. X squared is actually a great example of a concave up graph because it's always going to be concave up. You can see it decreases on the left side of the y-axis, increases on the right. F double prime is a constant in the positive region, so we know that the graph is concave up. Everything becomes flipped if we add a negative to the original function. But I think the best way to explain concavity is to look at sine waves. It's great because it's full of concavity. The first derivative of sine is cosine, and when we set cosine equal to 0, there are mins and maxes. The second derivative of sine is negative sine, and when we set negative sine equal to 0, here are the inflection points. We know that on the interval 0 to pi, sine is concave down. We can clearly see that. But if you take the second derivative, it's fully negative in this region. Inflection point right here at pi, which means it's a minimum for cosine, but now it is starting to go back up. And you can further push up with more derivatives, like the fourth derivative shows here that's negative sine x is concave up on 0 to pi, as the fourth derivative is sine x, and it is in the positive region. So let's move into applied problems, right? Kinematics? I don't know, I'm not taking AP physics or anything like that. It's not something I would do in senior year. But I know it's really important. So, we know that there might be inflection points here, here, and here. But what does that really say? If we took a train and it moved from point A to point B, it has velocity and acceleration. Velocity is the first derivative of position. Acceleration is the derivative of velocity, second derivative of position. Let's say that this train has a graph as it moves along, but it has to stop sometimes, maybe move it back a bit. Take s of t. Here's our velocity graph. Here's our acceleration graph. Inflection points are meant to show that velocity will hit its top speed. Remember, speed is the velocity put in an absolute value. So the velocity will hit a critical point. Then it will now begin to slow down a bit. slowing down more and more and more, and the train comes down to a halt when v of t equals 0. That's our critical point for s of t. Then moves in the other direction and begins to speed up in that direction. Or we can just really make this easier on ourselves and look at this x squared graph again, because it's so much easier to understand. Negative side, the graph is slowing down to a halt and speeding up. Negative x to x squared, slowing down, speeding up. To sum up, when v of t and a of t are the same sign, the object speeds up. V of t and a of t are the opposite sign, the object slows down. Okay, now I have a calculator section that goes over the problems that I have in my homework guided notes, so if you need to get used to the calculator, you might want to watch this. Okay, so now we're looking at question number 4 on the homework that I provided with your guided notes. It's an applied concavity problem where it moves across the x-axis. A particle moves along the x-axis. You find this on a lot of FRQs. You see it on a lot of FRQs. That's very important. When we graph this, we're gonna do it in respect to time t. Very important that you understand that when we go over this, it's not x, it's gonna be t. So that's our time. That's our independent variable. Anyways, let's look at our first question. A. What interval is s of t concave down? If you remember anything about concavity, remember that when we're looking for when anything is concave down, we look at when the second derivative is negative. Not positive, negative. Anyways, let's find the first derivative of this s of t, which is v of t, the velocity. Basic power rule stuff. 10.6 t. Wow, we just did the power rule. Great. Anyways, we're gonna do acceleration now, which is the second derivative, because we don't want to take the first derivative. We take the second derivative. So now we have the acceleration. We do the power rule again, guys. 3.6 t minus 10.6. Now that is amazing. Good job, guys. I know you can do it. Now, remember, second derivative, and it has to be negative. So, how do we find this? Because we can't just factor out 2.6 t minus 10.6. Impossible. Well, we have our handy dandy calculator. Isn't that amazing? So, first, when you have a calculator, a graphing calculator, you're gonna need this on your AP exam, very important. You find the on button, or else you can't function the calculator. Then, you take the y equals. This is how you plug in your functions. Now, we take, let's take our concavity graph. Wait, no, that's the second derivative, or acceleration. So we plug in 3.6, and I can't really find the t, so I just use x as a substitute. It doesn't matter much. Minus 10.6. Wow, that's great. Now, we do this funny little button called trace. And what does it do? It graphs it. Wow. But now, we can look for when x is equal to 0, so we can find the interval at which, since we're looking at the negative area, it keeps going up until right here. Now we want to find where this part is, so we can write down the interval. So we already know. Here, we'll do green for the acceleration. So we already know it stops around 3. Around there, but we want to be exact with our numbers. So what we can do is we can do second, and above trace we can do calc. Wow! Now you can do 0, enter, and it's gonna ask you for like a left bound or right bound. I mean, you can do that for other ones, but you would do that. And then for the right bound, you can do it. So, we're handy to end the calculator. We put like left bound over here. And then right bound there. Oh. And it's gonna ask you to guess. Yeah, just guess. And look, it says the 0 is at x equals 2.94444444. I don't want to write all of those numbers, so I'm just gonna say at this interval, it stops around here, which is x is, or in this case it would be t equals 2.944. So I'm gonna have to edit that out. Okay. So our interval when it's concave down is 0, 2.94. Wow, we did it, guys. Now we have 2 more problems left to solve. Okay. Now, at t equals 3.5, what is the concavity? This one's a real easy one. At 3.5, where is 3.5 at? Oh, I wonder if we look at 3.5, it's up here. Is that in the positive region or the negative region? I'm gonna give you 20 minutes to think about that. Time's up. It's in the positive region. So when it's in the positive region, it's concave up. Amazing. Amazing. Isn't that great? Now, here's a little bit more, something that's a little bit more complicated. At t equals 3.5, is the particle speeding up or slowing down? That's what kind of messes with me a bit. So stick with me. We're gonna graph our v of t as well. Because to figure out when it's speeding up or slowing down, we need to graph both a of t and v of t. So take our calculators again, y equals, and just we go down to the second y. So v of t equals 1.8 t squared, but I put an x, minus 10.6 t, or x in this case. So, and then we trace. Wow, fantastic! Anyways, if we were to graph this, where is that? I can graph things properly. That's something I can do. Okay. Wow, that's our velocity graph. Now, if you remember, anytime a of t and v of t are positive, our function is speeding up. But when a of t and v of t, when a of t is positive up here and our v of t is negative, it's gonna slow down. So technically, we are slowing down. And that's how you solve my fun little calculus problem, guys. Thank you so much for watching.